Okay, so our next speaker is Yusuf Mokrani, and he will talk about commuting Ramanujan graphs and the random self-reducibility of isogeny problems.
Hi, so this is joint work with my supervisor, David Zhao. So the question in our paper is relatively simple. Are SADH problems, SADH variants, randomly self-reducible? In other words, if you're able to solve the average case, are you also able to solve every single case? The reason we care about random self-reducibility is a lot of those SADH variants, including the original SADH, usually the first attacks on them make use of the endomorphism rank of the starting curve. And a natural way to defend against those attacks is to start with a random starting curve. But that implicitly, that implies that your problem is randomly self-reducible. Also, it opens new applications. In a theoretical sense, randomly self-reducible problem allow for example, new zero knowledge proofs. In a more applied sense, there are right now protocols for isogenies that, for example, chain isogenies, which would mean that like the second, third, and following isogenies in the chain starts with random curve, and you assume that this problem is randomly self-reducible if you want to work with them. Also, it's usually just good to know the properties of the schemes you're working with. So a quick overview of how we're going to do that. For our results, we need two concepts, gamma SADH, which was first introduced by DeFeo, Fuerza, and Pani, as well as the general concept of supersingular isogeny graphs. So we'll just give a brief introduction to those two concepts before giving our results. So the core isogeny problem is the supersingular isogeny problem, which simply states that if you're given two elliptic curves, E0 and E1, both defined over fp squared, are you able to just get an isogeny from E0 to E1? Usually, the actual problem you will see is you're also given the degree of a secret isogeny between the two curves, just because of how parameter sets work in practice. However, at least by itself, this information doesn't give you much. And in fact, if the degree is large enough, there will always be an isogeny of degree d between your two elliptic curves. This problem is, at least for now, considered to be secure even against quantum computers. However, if you don't leak any more information than this, it's pretty hard to find applications. So you have to leak something else. And historically, what was been done is SADH, where in addition of leaking the degree, the starting curve, and the image curve, usually it's not actually forced, but usually those schemes will leak the endomorphism rank of the starting curve just because it's easier to do so. But the main thing that SADH leaks is they take 2 points that form a basis of the end torsion of the starting curve and just give away the mapping of your secret isogeny on those 2 points. And now you're asked to find an isogeny from E0 to E1. Note that you don't actually need to find the exact same isogeny as the secret one. You just need to find one with good enough properties. And then SADH, the reason we care about it is that it has many applications, notably psych key encapsulation mechanism. And also, for example, you can do zero knowledge proofs with it. However, as many know, as most of you should know, it has been broken in 2022. So we cannot really use the SADH anymore. So a pretty natural construction to make is you have two schemes that both leak the domain and codomain of your secret isogeny, as well as the degree of said isogeny, where your generic problem leaks nothing else, while SADH leaks way too much. So it's pretty natural to think that maybe there's a problem that lies between those two that has a lot of applications, but doesn't leak too much to not be secure anymore. And to get this concept of gamma SADH, you have to realize that isogenies have a lot of properties. One of them is that they're group homomorphism. So if you're, because your degrees has to be relatively prime to n for your torsion, you can only map a basis to a basis. Which means that if you just take some random basis on your image curve, there will be some invertible matrix that will map the correct mapping to your randomly chosen points, which means that we can rewrite the generic isogeny problem as giving away 2 points that are the correct basis, the correct mapping times some invertible matrix, and we can rewrite SIDH to have this same structure by forcing the matrix to just be the identity. This concept is called level structure, where if you choose H to be some subgroup of the invertible 2x2 matrices and have this equivalence relationship where 2 ordered bases are equivalent if there's an invertible matrix in your subgroup that maps one to the other. So an H-level structure is just a class in this equivalency relationship. And then gamma SIDH is simply, you're given 2 H-level structures, you're told that there is an isogeny of degree D between those 2. Can you find one? And we can rewrite most SIDH variants in this gamma SIDH template. For example, the generic problem is what we call the trivial level structure, where H is the entire group. SIDH is the full level structure, where H is just the identity. If you want, for example, masked SIDH, you just take H to be the multiples of the identity. If you want a lot of zero knowledge proofs, give away a single point that is additionally masked, you can represent this with the Borel level structure, which is all of the upper triangular matrices. It could have been all of the lower triangular matrices. It doesn't really matter. And for example, Festa uses the split-Cartan level structure that can be represented by having all of the diagonal matrices. It's worth noting that you can reduce C-side to a similar problem just because the orientation that C-side leaks can be represented in this, but it's a bit different because, for example, in C-side, you cannot leak the degree. Okay, so now we'll just jump to the concept of supersingular isogeny graphs. The supersingular isogeny graph, you simply has as your vertices the set of every supersingular elliptic curve over fp squared up to some isomorphism. For example, this is the vertices for p is 79. And your edges, for example, if you have the supersingular isogeny graph, GL is just the L isogenies. For example, here's G2 and here's G3 for the same prime 79. It's worth noting that even when you change your L, the vertex set is always exactly the same. And an important properties of supersingular isogeny graphs is that you can represent isogenies of degree L to the S as walk of length S on the graph. If you want your isogeny to be cyclic, you just need to stipulate that your walk is non-backtracking. And for example, if you have an isogeny of degree that is not just a power of prime, you can work one prime power at a time, do a walk on the first graph, fix the last point on your first walk as the first point on your second walk, and just continue walking until you're done with your isogeny. The reason we care about supersingular isogeny graph is that there's this old theorem by Peiser that these graphs are Ramanujan, which just means that you have an upper bound on the eigenvalues of this graph. And also, if P is congruent to 1 mod 12, your graph is undirected. This will be important for our results later. If P is not congruent to 1 mod 12, you might have 1 or 2 curves in the entire graph that cause issues. The reason we care about the graph being Ramanujan is that there's this theorem by Zhao, Miller, and Varkatesan that if you have an upper bound on your eigenvalues, for example, in case of supersingular isogeny graphs, and you do a random walk on starting on a fixed vertex, then the distribution of the end vertex on your graph will converge to a uniform distribution. And we can generalize this concept of supersingular isogeny graphs for level structure. All you have to do is change the vertex set to also have level structure. The edges are defined the exact same way. And there's this recent theorem by Codini and Lido that when you choose your level structure, if your subgroup contains every invertible matrix, every invertible multiple of the identity, as well as a matrix of every possible invertible determinant, then once again you have a Ramanujan graph whose AJCC matrix is diagonalizable. So now we have every tool to see the random self-reducibility reduction. The reduction itself is pretty simple. What is hard is just to prove that it works. So you have this secret isogeny from E0 to E1, and you want to find it or find one between those two curves. All you have to do, if you're able to solve the average case, is just you sample a random isogeny from E0 to, let's say, E0 prime. You sample a random one from E1 to E1 prime. And now, because of the properties of the supersingular isogeny graph, those are two random elliptic curves. This is the average case, so you can just solve it. And now all you have to do is chain your 3 isogenies, and you now have a solution to every single version of the problem. However, in gamma SLEH, not only the degree is important. So if you're able to somehow solve only for a small degree d, because this theorem by João Miller and Varkatisen tells you that the distribution of a random walk is uniform, if your degree is too small, you have a real risk of just ending in cases where you cannot solve it because there is no isogeny of degree d between your 2 random elliptic curves. So what we have to do for this reduction to work is to prove that for some value of d, then a random isogeny is able to reach a non-negligible fraction of every single vertex. And this is the main result of our paper, which is a generalization of a paper by Sardani that states that if you're given a family of k Ramanujan graphs, where our isogeny graphs apply, that have the same common vertex set. Once again, our graphs apply. With the following properties, we need that the AJCC matrices commute between each other. This directly comes from properties of isogenies. We need that the graphs are Li plus 1 regular with diagonalizable AJCC matrices. So long as we have the Codogny-Lido conditions, this will once again hold. We need that the GCD between the different LIs are relatively prime. By just taking the LIs to be prime, this will always hold. And finally, we need, this is the biggest eliminator, we need every graph to be undirected because we need the AJCC matrix to be real. And we need the AJCC matrix to be real because we need the eigenvalues to be, we need the AJCC matrix to be symmetric because we need the eigenvalues to be real. So the only real way we can force this to be true is to just have P is congruent to 1 mod 12. And if we have everything here is hold, we have this fun little lower bound that, at least for our concept of isogeny, just gives us a lower bound on the number of elliptic curves that can be reached from a fixed elliptic curve using an isogeny of degree d. So how does this result apply to our SLEH variance? Once again, it only applies if we have if these 2 conditions by Codogny and Lido apply. So if we try to apply them, for example, in the generic problem, it applies pretty easily since the level structure just contains every single matrix. For SLEH, the result does not apply since we only have the identity. SLEH is a bit of a weird case since when in parameter sets where SLEH is broken, it is randomly self-reducible by default. But when, for example, it doesn't apply, we cannot prove random self-reducibility. So it is worth noting that we cannot prove that a problem is not randomly self-reducible. We can simply only find cases where it is. MSLEH is close to having everything we want. However, sadly, it does not contain matrices of non-square determinants. How it ends up working is that the isogeny graph associated to MSIDH usually will be bipartite, which means that a walk of fixed degree can only end in one of the two partitions, so you don't have uniform distribution. For future work, it might be interesting to see if we can solve this issue by using non-fixed degrees. For example, MDSIDH does that. For the Borel level structure, our results apply. And for the carton level structure, our results apply. Now the question is, okay, the results apply, but like for what parameter sets? So if we just write the factorization of n and d for our parameter sets, it ends up, for example, in the generic case, our results apply so long as this fraction is non-negligible. And essentially, this will happen whenever d is about the same size as p. Okay, so when we do, for example, the Borel level structure, the fraction gets much more complicated just because now the value of n is actually important. If you want like a rough estimate on when this is non-negligible, if you assume, for example, that d and p are both just prime powers, this will hold whenever your degree is about the cube of the size of n and at the same time about 3/3 the size of p. And for the carton level structure, it's similar. This time you need your degree to be 4 times the size of n and twice the size of p. So in conclusion, we are able to prove that, for example, we can find parameter sets for which carton and Borel level structure variants of SIDH are randomly self-reducible. Those parameters are a bit too large for current parameters. However, it's only by small factors, in our case being 3 and 4. There's many avenues of possible future research. For example, like we said, MSIDH could possibly be salvaged by not working with a fixed degree. The bonds can probably be improved since in our results we work with Chebyshev very old bonds on Chebyshev polynomials that can probably be improved now. And finally, we require that P is congruent to 1 mod 12, which is probably not actually required, since the issue only comes in for at most 2 vertices in a graph of cryptographic size. Thank you for listening. If you have any questions.
Thank you, Yusuf. Do we have any questions? Okay, I'll start then, and let's see. So yeah, you mentioned that for MSIDH, this doesn't, your exact proof doesn't apply yet. This is mostly due to the properties, right? Or do you think this is indicative of vulnerability that you need to look into?
I mean, the thing about MSIDH, because of how it works, because it can never give a non-square matrix. If you just sample 2 random points on your isogeny graph, half of the points will not have a mapping that actually exists. So I really think that like all you need to do to deal with MSIDH is just maybe allow your degree to be slightly different. And like there is literally an actual version of MSIDH that does that, which is MDSIDH. And I think there is a reduction from MDSIDH to SIDH. So maybe there is a reduction where you prove that you reduce MSIDH to MDSIDH, prove that MDSIDH is randomly self-reducible, and then go back to MSIDH.
Yeah. So is the big problem that you need like a fixed degree isogeny? Because otherwise, like the way that you showed the reduction, can you solve something about the degree being different with KLPT, right? Because you can find a isogeny of a high degree using this oracle.
We're trying to not need the starting endomorphism ring, which makes KLPT unusable.
Yeah, you don't want that. Okay, yes. Any other questions? Yes, I see you're pointing to someone. Yeah.
Are there any contexts in any variants where you can prove that they're not randomly self-reducible if you are allowed more than 1 degree?
At least with the techniques we use here, we cannot prove that something is not randomly self-reducible because you would need to prove that there is no technique we're not seeing right now that would work. So we can only find positive results if we use the techniques in our paper.
Do we have more questions? I don't see anyone, so yeah, let's thank Youssef and both speakers of this session again, please.